So another major fire zone for an aircraft is its power plant, that's the engine, because it's the main cause for thrust of an aircraft, so may catch fire. One of the fire zones is the lavatory inside the aircraft. So some hard-headed passengers try to smoke inside the lavatory zone, since there's no smoke detectors. They tend to smoke inside. That's why the lavatory is one of the fire zones inside the aircraft.
In this lesson, we will discuss the fire detection systems fitted to all aircraft. A fire cannot exist without three things being present. These are heat, or a source of ignition, fuel, material that will burn, and oxygen. This is known as the triangle of fire. Take any one of the three away and the fire will go out. A fire in an aircraft is extremely dangerous. So to protect the aircraft, the crew and the passengers, aircraft must have fire detection and extinguishing systems fitted in all areas where a potential fire risk may exist, following failure of or leakage from any component or associated equipment. The specific areas that require protection are the engines, the auxiliary power unit or APU, the main wheel wells, and the cargo compartments. These areas are known as designated fire zones, and they must have detection systems fitted to warn the crew of a fire. In the case of the engines and the auxiliary power unit, they are isolated by fireproof bulkheads, known as firewalls, normally manufactured from titanium or stainless steel, which will contain any fire to the immediate area and prevent it from spreading to the rest of the aircraft. Each designated fire zone must have a fire detection system which is capable of providing rapid detection and warning of a localized fire or overheat condition. There are a number of detection systems in use, and we will now take a look at them. Differential expansion detectors use the fact that when heat is applied to different materials, they will expand at different rates. A detector consists of a pair of contacts mounted on a spring bow assembly fitted within an expansion tube, which is mounted on a base. The spring bow is fixed to the tube at the top and the bottom. When heat is applied, the tube expands at a greater rate than the bow, drawing the contacts together. When the contacts come together, they provide power to the warning circuit. A subsequent drop in temperature will cause the tube to shorten, the contact to open, and the warning to stop. This type of detector usually incorporates a short time delay before the warning is activated, to prevent false warnings due to vibration. Differential expansion detectors are often used to monitor engine cooling air outlets in order to provide internal engine overheat warning. In the event of this warning being given, the pilots will normally be required to shut down the engine. Engine and auxiliary power unit fire zones are often fitted with continuous loop fire detectors, commonly known as firewire systems. A detector unit consists of a stainless steel tube with a central electrode insulated from the tube by a core of temperature-sensitive material. Firewire detectors operate on the principle of their core material having either a negative coefficient of resistance with temperature or a positive coefficient of capacitance with temperature. In one system, both methods are used together. In the resistive type of firewire, as the temperature increases, the resistance of the insulating material decreases. This causes the current flow between the central electrode and the outer tube to increase, until, at a predetermined temperature, sufficient current will flow and the warning system will operate. If the temperature drops back below a preset value, the system will automatically reset, and the warning will stop. This type of detector will react and give a fire warning if there is an isolated temperature increase, for instance from a direct flame, or if the temperature of the entire detector increases, possibly because of a hot gas leak. Because the loop is connected to the control unit at both ends, the system will continue functioning with a single break in the firewire. One particular problem with this type of system is that a short circuit between the case and the inner electrode will give a false fire warning. In the capacitive type of system, the detector acts as a long capacitor, with the core material acting as the dielectric, and the case and the inner electrode as the poles. The case and the inner electrode are connected across an AC supply. An increase in temperature causes a change in the properties of the inner core material. This change increases the capacitance of the detector. The firewire is polarized by the application of half-wave rectified alternating current from a control unit, which it stores and then discharges as a feedback current. As the capacitance increases with temperature increase, so will the feedback current. Once the feedback current reaches a predetermined level, it activates the fire warning. As with the resistive type, this system will reset itself once the temperature drops below a preset level. This type of detector will also react and give a fire warning if there is an isolated temperature increase, for instance from a direct flame, or if the temperature of the entire detector increases. Again, as with the resistive system, the loop is connected to the control unit at both ends, so the system will continue to operate normally in the event of a single break in the fire wire. This system has the advantage over the resistive type in that a short-circuit grounding of the element or system will cause the capacitance to fall to zero, so will not result in a false warning. Fire wires are positioned around engine fire zones in a continuous double loop.